Hello. We've seen already the connection between area and a definite integral and how we can use a definite integral to find the area between a curve and the x-axis. But now we're going to look at how we can use definite integrals to find the area between two functions. So if we want to determine the area enclosed by y equals 9 minus x squared and y equals 6 minus 2x, we are looking for the area, in other words, between these curves. Essentially, what we can do is find the area under the top curve and the x-axis, and then find the area between the bottom curve and the x-axis, so what I've marked in green here, and we can subtract them. So this is going to require us to know the intersection points. These ones are already labeled, but you could find these intersection points algebraically. It's a quadratic equation, a factorable in this case, or you could use the quadratic formula. But essentially, we are looking for the area between x equals -1 and x equals 3. So we're looking for the definite integral from -1 to 3. The x values are the relevant ones here. And the top function, the sketch also helps me see which function is on top. The top function here is the 9 minus x squared. The bottom function is the 6 minus 2x. So I need the difference between those two functions. So this is essentially the integral that we need in order to find that area. You can write this as two separate integrals. The integral from -1 to 3 of 9 minus x squared dx minus the integral of -1 to 3 of 6 minus 2x dx. But we might as well write it as one integral and actually simplify that polynomial before we antiderive. So I've got -x squared plus 2x plus 3 dx, which means that my antiderivative, -x cubed over 3 plus x squared plus 3x between -1 and 3. So my area is going to be, when I substitute the 3 in here, I get -27 over 3 plus 9 plus 9. When I substitute the -1, I get 1 over 3 plus 1 minus 3. And so when we actually do this whole thing, these ones are going to cancel out, so that's -9 plus 9. I get 9 minus 1/3 minus 1 plus 3, which is, as a final fraction, 32 over 3. So the area is 32 over 3. Now, we should definitely always get a positive value here for area. So if you get a negative value, you've possibly subtracted your functions in the wrong order. So just double check. We have to be very clear that we're subtracting the top function minus the bottom function. This gets a little more complicated if you have multiple intersection points. So if we want to find the area between y equals sine x and y equals cos x over one period. So technically that period could start or end anywhere. If we went from 0 to 2 pi, we would be looking at this little piece of the area here, this whole section in the middle. Somebody once told me they look like sausage links, and I kind of can't shake that image. So this sausage right here, and then up to 2 pi, this sausage right there, but only part of it. Although, if you're thinking about it and you realize what you know about trigonometric functions, you know that there is symmetry here. So in fact, I could just extend this a little bit and use this region while ignoring this region because they are equal. Or if you think about it, if I take just this area and multiply it by 2, I am going to get the right area. Either way, I'm going to need to know the intersection point. So I'm just going to find the area I've marked with A, and I'm going to double it. So I need to know where they intersect. Now again, where are cosine and sine equal? They're equal for reference angles of pi over 4, or 45 degrees. And in fact, the first one is going to be at pi over 4. The next one is going to be where they're both negative. So in other words, in quadrant 3, with a reference angle of pi over 4 is going to be 5 pi over 4. So my two intersection points that are relevant here, the area is going to be 2 times the integral from pi over 4 to 5 pi over 4. And the top function in this interval, the red one, is the sine function. So sine x minus cos x dx. So 2 times antiderivative of sine x is negative cos x. antiderivative of cos x is sine x. So here is the antiderivative between pi over 4 and 5 pi over 4. When I actually substitute in these values, so I get the area is, again, it's going to be 2 times this when I'm done with it. So negative cos 5 pi over 4 minus sine 5 pi over 4 minus negative cos pi over 4 minus sine pi over 4. All right, here's where you have to be really careful with all these negative signs. So the cosine of 5 pi over 4 is negative root 2 over 2, but it becomes root 2 over 2. And same thing with the sine. The sine of 5 pi over 4 is also negative root 2 over 2, but it becomes plus root 2 over 2. And because here I have minus all these minuses, they are just positives. Cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. So essentially what we end up with is 4 times root 2 over 2, which is just 2 times root 2. And we're doubling it, so the area is 4 root 2. I doubled it twice in my head by accident. 8 root 2 square units. That is the area between the curves. Even though that's a discontinuous area, as long as we use the intersection points to divide it up, we will find the right area. So now, determine the exact area enclosed by y equals sine of 2x, that's the one in red, and y equals secant squared x minus 1 on the interval from 0 to pi over 4. So that is just this area enclosed here. And they've helpfully already told me what my upper and lower limits are, so I do not have to find intersections. It is important to know which one's on top, though, so that's where the graph is usually helpful. So the area is going to be from 0 to pi over 4. The top function is the sine of 2x. The bottom function is the secant squared of x minus 1, but since I'm subtracting it, it becomes plus 1 dx. All right, so I need an antiderivative of this. So antiderivative of sine of 2x is going to be negative cos 2x over 2. Because if I derived that, I would get the times 2 for the chain rule. Antiderivative of secant squared of x is the tangent of x, and an antiderivative of 1 is x. And we need to evaluate this between 0 and pi over 4. So negative cosine of pi over 2 over 2 minus the tangent of pi over 4 plus pi over 4, and then minus negative cosine of 0 over 2 minus the tangent of 0 plus 0. Now, the cosine of pi over 2 is 0, so this one goes away. The tangent of pi over 4 is 1 plus pi over 4. And we've got the cosine of 0 is 1, so this becomes negative 1/2. But we are going to subtract it, so it is going to become positive. Tangent of 0 and 0, those are just zeros. So what we get ultimately, and we want an exact value, so I'm not going to try and simplify this. I get negative 1 plus 1/2 plus pi over 4, or in other words, pi over 4 minus 1/2. So even though I want the exact value, it is worth verifying that that is a positive value, and it is because pi over 4 is bigger than 1/2. But that is the exact area here. You can find practice for these in the